And now it's time to look at the other indeterminate form. Because as I have said earlier when we beginning with this lesson, then 0 over 0. So both 0 in the denominator and numerator, or both some kind of infinity in our denominator and numerator, those are not the only two indeterminate forms out there. So now we have some other indeterminate forms here. Okay, and so I have to be clear before we get into finding limits on any of these indeterminate forms. L'Hopital's rule will not work directly on any of these indeterminate forms. That's why it was me and any other instructor who teach this specific topic have to start out with the two important ones. The 0 over 0, either both zeros in the numerator and the denominator, or both some kind of infinity in the numerator and the denominator. So these are the only two indeterminate forms where L'Hopital's rule can apply. But then any of these I'm about to introduce, the L'Hopital's rule will not apply directly, but we will find ways to have sort of work around. Okay, but now let me explain what those other indeterminate forms are first. So, as it turns out, when you take your limits and basic limit laws lead you to a 0 multiplied with a positive with an infinity, some kind of infinity, that is actually an indeterminate form right here. Now, normally a lot of time people would rushly think that this could be, hey, 0 multiplied with any quantity as a 0, but it's actually not. Okay, 0 multiplied with infinity here is actually an indeterminate. Okay? Think about, because this is going to 0 only. It's getting small. It's not really a 0 quantity. It's just something that's getting small, and this is something that's getting big. So getting small and getting multiplied with something getting big at the same time is not necessarily going to be an overall 0. Okay, so this is one of the indeterminate forms. Another one right here that's also easy to make mistakes right here. An infinity minus infinity. This is another indeterminate form. I over my time teaching, I keep having students mistakenly subtract infinity from infinity and cancel out and get a 0 value as the final limits. This is not the case. It just means, think about two functions. Each one of these both grows to infinity, but they're being subtracted. So they don't always see. We talked a little bit before this point about dominance. So, well, no one can guarantee that these two functions always grow at the same pace, so that we can cancel out and be turn out to be nicely equal 0. And so, in other words, yes, even though the symbols looks the same, infinity minus infinity, but we can't just simply cancel out, because that difference there between two growing up functions can still be something other than 0. Okay. One quick little example to demonstrate how wrong it is to take this as a 0 over here. It's very wrong, because think about x squared minus x. Both of these functions, if we're taking the limit as x goes to positive infinity, okay, then this term x squared itself, that goes to positive infinity, but we're going to, according to basic limits law, we can also apply a separate limit for x. Both of these terms go to positive infinity. We're subtracting. So, but the answer wasn't 0. The answer for something like this was positive infinity. Okay. So I just want to quickly point out how incorrect that is, to rushly cancel out the two infinities here. So it's not only because your teacher up here is saying so, then you have to take that, but there's reason why we treat this as an indeterminate form, because sometimes it could be a positive infinity, sometimes it could be something else. Okay, and then there's a few other ones. So let's say we can also have a 1 to raise to the infinity power, and then we can also have a 0 to the 0 power. And then we can also have an infinity raised to 0 power. These are the other indeterminate forms. So we have about 1, 2, 3, 4, and 5 other indeterminate forms outside of those that we can apply the L'Hopital's rule directly. So again, L'Hopital's rule does not apply on any of these directly, but there will be workaround for us. That means we can still find the limits if we run into any of these problems, but not necessarily directly using L'Hopital's rule. Okay, so now when it comes to these and the way to handle these problems, there is no hard rule, and there's no hard how-to instruction of how to get through with these problems. So that's why I aim to give as many problems as I can, and once you are done with my videos, feel free to hop onto YouTube or hop onto the Google. There are tons of resources out there, and learn from other professors, so that you can learn as many styles, and so that eventually all that experiences will become yours, and then you will become more quick in terms of solving these kind of problems right here. Okay, so learn from me and also learn from other professors. So let's look at example 3 right here, and I can only point out about 2 little problems in this example 3. So let's evaluate. Okay, and our first one to come here. So how about I'm looking at part A, x times a natural log of x, and we want to take the limit as x approaching 0 from the right hand side. Okay, so this is how I see it. A quick little analyzing look into this function right here. Then, well, analyzing this, what I see now is that the rule for taking the limits of a product, right? Limits of a product rule is saying that we can run into the limits of x by letting x approaching 0, and take the product with limits of natural log of x, okay, by letting x to 0 again, and we can have these 2 separate limits multiplied together. That's the rule for taking limits of a product. So that means so this is basic law right there, basic limit laws. That limit here is a 0, because we're getting smaller from the right hand side of 0. We're letting x getting close to 0 from the right hand side, and so this overall is a 0. We should have known that by heart up to now. Now, as x is getting close to 0 from the right hand side, our natural log function is looking like that, and you're not really required, but understanding the graph of these things also help big time. Okay, so as you're getting closer to 0 from the right hand side, your natural log of x function actually drops to negative infinity. So negative infinity is here. So you're actually in this family, this problem here, you're in that family of the indeterminates, 0 times some kind of infinity. So I wrote infinity here in when I was introducing that form, but it also means it could be a negative infinity here as well. Okay. So that means here we have an indeterminate. So now, for this particular problem, here's how we can find. And like I said again, the L'Hopital's rule does not apply immediately, meaning don't do this. Take the derivative of x, gives me 1. Take the derivative of that, give me 1 over x. It might come out looking correctly, but it's not the way. Okay, maybe it works for this problem, but it generally won't work for other problems if we run into this kind. So be careful. But there has never been no approved rule of doing this. Take the derivative of the first one in the product, take the derivative of this next one in the product, set it up as a new problem, and take the same limits here, trying to work like the L'Hopital's rule. That's what I meant by apply the L'Hopital's rule directly. There's no L'Hopital's rule for this, and if you're doing it that way, it's probably your own rule if you can prove it. Okay, but this is how I'm doing it. This is how this problem can be handled. So I am going to, you see, you can have 2 choices. You can either go with rewriting this, and it needs your algebra skills here a little bit. This product x times natural log of x, I am going to rewrite it as an natural log of x over 1 over x. Okay, pause the video and do your algebra work, okay, to verify my algebra work up here. But this same product, can be rewritten as natural log of x, but over a 1 over x. All right, so hopefully you're back and agree with my setup right there. But now, after you agree with my setup, you're starting to wonder and feel insecure. Why am I leading you into the work that looks even more complicated than how it started in the beginning? But there's a good reason now. Now, alternatively, you can also rewrite the same expression as x divided by 1 over natural log of x, either one of yours. Either one of the way here. Okay, that's just algebraically correct. Each one of these expressions will equal that beginning one. Okay, and so now going with either of these two ways is going to be just fine, but this way I'm more comfortable with, because this is how I see it. So obviously the limits here in this problem is the same as the limits here of this problem. X is approaching 0 to the right hand side. I mean from the right hand side. And now quickly check. That means on the top, limit of natural log of x, as x coming close to 0 from the right hand side, and limits here in the denominator as x going to 0 from the right hand side of the 1 over x. Then in the numerator we ended up with that negative infinity, as we already have seen in the quick little graph I drew earlier, and the denominator here is the infinity. Okay, if we're rewriting our function that way, then we run into an indeterminate form. And like I said, don't worry about the negative sign as long as we have some infinities being involved in both numerator and denominator here. Then that's where we call it. It's one of the two fundamental indeterminates where L'Hopital's rule can apply it here. Okay, so let me take a quick pause here. I'm going to quickly turn over to the other board and do a quick scratch work. What if I went the other way? We could have also written that as x over 1 over natural log of x. That works too. In a sense that if we're taking this limit, okay, as x is going to 0, then limit law says the numerator goes to 0, and the denominator here, you see just the natural log of x itself go to negative infinity, but 1 divided to something that keep growing, it's go to 0 as well. So this is another indeterminate form that you can eventually use a L'Hopital's rule. Okay, so you have viewers out there and even students of mine, you actually have your choice of either going with re-expressing your beginning function into this form, or re-expressing your beginning function into the other form. Okay, and either one of these is gonna now allow you to use the L'Hopital's rule. Okay, but as I admitted earlier, I'm more comfortable with this route right here. Okay, so now we're clear that we know that we're at an indeterminate form right here. Now I am going to, so that's the verification work. It's required. It's just me up here. My board is so narrow, so I gotta erase that and put in the actual step now. All right, so now we can apply the L'Hopital's rule. So as long as we are running right into the indeterminate form, the L'Hopital's rule says now I can create a brand new problem where numerator of my new problem came out from the derivative of natural log of x. So it's now 1 over x. And I'm going to also generate a new function which came out from as derivative of this 1 over x. So that derivative of 1 over x is negative 1 over x squared. Okay, 1 over x over negative 1 over x squared, and set it up in the same order of the fraction, and now consider it as a brand new limit problem, but still looking at limits going to the same limit points like that. Okay, and so now we can start doing some algebraic manipulation here, algebraic simplification. So 1 over x cancel with all that, and it's going to be, so it's a 1 over x times it's a negative x squared now. It's just the rule of algebra. Okay, and we're taking the limit as x approaching 0 from the right hand side. So x squares cancel with that and leaves me a minus x. Okay, and now we're taking the limit minus x. And now we're taking the limit as x is approaching 0 from the right hand side, and so the overall answer here is a 0. So now This is the answer to this problem, but according to L'Hopital's rule again. Now this is, you see, indeterminate in a way that it's, so according to L'Hopital's rule, it's the same answer with that, even though we gave up with that, because that's right there is an indeterminate. Okay, but now our conclusion here is this final work here is 0. The final limit for that is equal to 0. So back to what I said, I did not use any kind of try to be like the L'Hopital's rule to take the derivative here and take the derivative there, take the derivative there, and multiply the two derivatives together and hopefully apply the limits as two separate limits. No, it's not that way. Okay, we don't have a direct L'Hopital's rule, but the trick I did here is I take one of the function. So this is what I recognize. So I can only say that this is a common style of how people can approach this, but that's not the only way. Okay, yes, a good majority of people going this route. The little experience I found in this problem is, you see, we got one function being in product with another one, and that's the whole reason why we can eventually end up with one of them being a 0 and the other one being an infinity. Then we can algebraically re-express this as either a g over a 1 over f of x. That's one way. Okay. Or, so take note carefully or pause the video if you have to. But that's not the only way. The same product here, f times g, you can also rewrite that as f of x, but over 1 over g of x. Okay? And so that's what happened here throughout my work with them. Okay, but again, as I said, this is not, I mean, it's the one that, you know, most commonly working out there, but that's not the only way. So you just have to start exploring into your own creativity. And when it comes to a creativity, being an instructor here, I can only show as much experience of mine as possible. And then hopefully you can learn from it. And of course, learn from other professors. These kind of problems right here are quite standard, and they got tons of problems and examples over the web right there for you to read through or view through YouTube videos and all that. Okay? And so now, let me bring you into another problem. Okay, so same example 3 right here, part B of our example. Let's look at, how about my function here is, okay, let's take the limit as x approaching positive infinity. And here our function is x squared times e to the minus x. Okay, x squared times e to the minus x right here. Okay, so here's the observation. Again, I have a product. Okay, and if we are using the basic limit law right here, then this function goes to infinity, and the other one here goes to 0. Okay, e to the minus x. We take the limits as x go to positive infinity. This is actually going to 0. Why is that? I mean, just a quick little scratch work, but why is that? Because e to the x, e to the minus x itself is 1 over e to the x. And so taking this limit is the same as taking the limit as x is going to infinity for 1 over e to the x. But so in the numerator, it's a constant, and my denominator here keeps growing big and growing big. Back a little while ago when we were still doing the kind of problem where we were specifically learning about limits to infinity right here, then I brought up that quick little scenario about one pizza, but the number of people who are interested in taking a piece of the pizza is increasing. So say there's one pizza, but 4 people want it, then each one get a fourth, right? That's how we got division problem came out from. But now, unfortunately, about 8 people want it, and then so if we really have to divide, right? So the number in the denominator grows more. That's what it is. So each one here, as an overall quotient, is getting smaller. And so if there's 1 million people who want the pizza, then anyone is just get just maybe a single taste of the pizza right here, not even a bit. And that's the idea. Overall quotient will become 0 when anytime numerator is constant and the denominator grows bigger and grows bigger. continuously. And so in that way, now we knew that this e to the x, e to the minus x, as x approaching positive infinity is 0. But then the other part of our function, x squared, we already learned by heart that this is going to be a positive infinity. So in the end, now I just want everyone to realize what we have here is infinity times 0, which is, and that's the reason why I classified this problem under this class of problem right there, is 0 multiplied with positive infinity. Okay, but so here's the thing. This problem actually is a lot simpler, even though I put that as part B, but it's a lot simpler than the one we had earlier. Yes, it's a product between the f and some. This could be f, this could be g. You can do your trick about that, f over the 1 over g as one way, or you can put your function as g, your overall problem as g over 1 over f of x. That could be one way, but let me now tell you, this particular problem, we don't have to go even that far complicated. Okay, we don't even have to go that far complicated. Even though we could, if you decide to go with that common way, but here as I said, I just want to show you people as much creativity, how creative you can be right there, and then you take from these learning from me and from other professors, and you can one day become creative on your own right there. But you see, when I actually wrote that earlier, e to the minus x is the same as 1 over e to the x. Take full advantage of the algebra that you've had. Your algebra is, if you have a strong foundation on the algebra, you will sure be able to go real far in your mathematical career right there. Okay, so this is how it gets. Limit of as x goes to positive infinity. But now this expression, I'm going to write it as x squared times 1 over e to the x. X squared times 1 over e to the x. And so we can simply put that together in one fraction. So now I'm looking at x squared over e to the x. As taking limit as x is going to infinity. And so now clearly something like this is landing right into an indeterminate form where we can now start applying the L'Hopital's rule. Okay, so L'Hopital's rule apply here, not right there. Okay, so now here's how I'm applying the L'Hopital's rule. So I'm going to turn my direction to using the L'Hopital's rule. The same work here, that same work there is the same as derivative of x squared is a 2x. Okay, it's sort of like we're generating new functions. It's 2x over e to the x. This e to the x is my derivative of this e to the x here. Okay, and now we're going to take the limits as x goes to positive infinity. Okay, but unfortunately this work so far is still giving me infinity over infinity. Then that means very similar to the example I introduced way earlier. If we run into indeterminates again, after we already used the L'Hopital's rule once, we apply the L'Hopital's rule again. Okay, because here we're still looking at an indeterminate. Okay, because again, we can take the L'Hopital's rule not only once, as many times as we want. Okay, so now that means a L'Hopital's rule again. I'm going to apply another L'Hopital's rule, and here I'm going to create another two functions. 2 coming out from the derivative of 2x, e to the x coming out as the derivative of e to the x. And now take the derivative. Take the limit as x approaching positive infinity. And now my work turns out 0. Now I have a successful finite limit. And so this limit here is equal to that. But L'Hopital's rule say it should also equal the same result with the step earlier. And L'Hopital's rule says that means if this limit now equal to 0, it should equal to the limit here that was equal to 0, which in the beginning was indeterminate form infinity over infinity. And so now I can go back to this problem here, and the final answer is equal 0. Okay, and that's how so I didn't have to go with that complicated work and turning that into an e to the minus x over 1 over x squared. We could, but why go, wasting so much effort where we can do something simpler. Okay, and being simpler surprisingly sometimes can be working a lot better. Okay, so in the end, if you can review as much algebra as you can, then any of your learning in calculus and even much further in mathematics will be a lot easier for you. Okay, and so now that is all about all I wanted to deliver for example 3. Let's head out for another example where I bring you into a different class of problems right there. So we are still evaluating. We're still evaluating limits. This time, let's look at example 4 here. All right. So how about in my first problem here? Let's call that part A. And again, my plan here is I'm about to deliver 2 problems. Okay. And once you've learned some from my lesson here and seen how I've done that, hop on the internet and find out how other professors have their own problem and solve their own problems, and you can eventually formulate into a certain experience for your own. Okay, learning is all about building things up from experience. So, how about my function here is x times e to the 1 over x minus x. Okay, and we want to take the limits as x is approaching positive infinity. Okay. And so now, here's how I see, this is what I see about this problem. Okay, we got a subtraction right there. Okay, we got a subtraction right there. That term is obviously going to infinity. Yes, that term. And then what about that term? Let's do a quick little math for here. But limits of x to the e times e to the 1 over x, as x is going to positive infinity. Now, this is the same as, you see, that term is going to positive infinity. This term here is going to e to the 0, because you see as x grows big and grows big, the 1 over x here becomes a 0, but e to the 0 is 1. So infinity times 1 is really just infinity. So that means we unfortunately now running into infinity minus infinity. Ladies and gentlemen, this example 4 here, I purposely showed you a couple experiences about how you handled infinity minus infinity, that indeterminate form right there. Okay, so again, please do not apply the L'Hopital's rule immediately here, not yet. And so here it becomes even more unclear about a direction to go. Usually, big time, people fix the problem, the situation by factoring out. Okay, so that we can factor out common factor, which I notice here, or sometimes we can combine. Sometimes it could be 2 fractions subtracting each other, and we can bring it all into 1 fraction, and then we can. So we do all the algebra works we can to eventually bring us to a place where we can apply the L'Hopital's rule, but just simply we can't apply the L'Hopital's rule right here. Okay, so here's what I see. So here I can factor out the x. Okay, and turn our expression into e to the 1 over x minus 1. Okay, and this problem here is a limit as x going to infinity. Okay, so now notice, now I turn that into a product. It leads me into another indeterminate in a sense that this guy x right here goes into infinity, but this term, these 2 terms together inside of the parentheses, you have seen my arguments earlier, then as x gets larger and larger, then 1 over x overall turn to a 0. And so e to the 0 minus 1 is actually 1 minus 1, which is 0. So here we have another indeterminate, infinity times 0, that we have learned a little bit how to manipulate back in example 3. And so now, but still, this is not where we can apply directly the L'Hopital's rule over here. So here's what I'm doing. Back to that similar trick that I so-called common, more commonly people use it. And here I'm going to stick with that trick as well. I'm going to turn my expression here into, well, e to the 1 over x minus 1, but over 1 over x. See, I'm doing that trick right there where I'm seeing f of x times g of x. I'm putting one of them into the reciprocal. So turn that into a quotient of the one function over the reciprocal of the other one. See, keep one function in the numerator and over the reciprocal of the other one. That's the way how it works, like that. So this trick works here pretty good. All right, so So now apparently when we get to this step, let's check it again. Now I know that, now I can see that I'm running into 0 over 0. Because see, that term I have argued quite a few times already. This term here, in particular, e to the 1 over x, is going to be a 1. Because that 1 over x here will go to 0 as x grows big to infinity. And e to the 0 is 1. So 1 minus 1 gives me a limit 0. This here again gives me a limit 0. So we now have a clear indeterminate form where L'Hopital's rule will apply here. Okay, so now noting that L'Hopital's rule, noting that the indeterminate form, let's now get directly into that. I'm going to create a new set of function. So according to the L'Hopital's rule, okay, then we are looking at so e to the 1 over x multiplied by the chain rules minus 1 over x squared. That's how I take the derivative of the first term. The second term in my numerator becomes 0, so I don't have to bother writing it. Now the derivative of my denominator here is negative 1 over x squared. Okay, and then we're going to take the limits. See, it's now a completely brand new setup, a completely brand new problem. Right, but now with this problem, it gives us a very good advantage. I can cancel directly that expression minus 1 over x squared. And that now gives me e to the 1 over x. And now limit laws can just simply tells me that this limit will simply equals a 1. Okay? See? So whoever is thinking about canceling infinity with infinity, that's going to lead you to a 0. Very incorrect from the actual answer here being 1. And so don't do that. Stay away from canceling out the two symbols that look like the same variable or same expression. They are not. Okay, so now our final answer here is 1. So this means all that here is 1. That's way back, the beginning, way back from. That's 1. Okay. All right, so now let's look at another problem here. In this class of indeterminates, an infinity minus infinity indeterminates form. So what about in part B, we are looking at an x minus natural log of x. Okay, and we are taking the limit as x approaches positive infinity again. And so with this problem, so apparently speaking, this is infinity, because as x gets large to infinity, then this term goes to infinity. This other term also, see, logarithm function is looking like that. And even though it grows slowly, but it's still growing, it will keep getting higher and nothing is going to stop it. Okay, and so that means here we run into another, see, clearly infinity minus infinity. And so, but still, no much luck for a direct L'Hopital's rule to be applied here. And so now we are going to turn our focus into doing some algebra work. I am going to stay with the same trick I've done earlier, even though we don't really see common factor, but how about I'm going to purposely see this x here as a common factor. So I am going to factor out x. So now inside of my parentheses here, I'm looking at 1 minus natural log of x over x. And now I'm going to take the limit as x approaches positive infinity, as x is heading out to positive infinity. Okay? And so let's look at each of these. The x here gives me an infinity. Okay? And then inside of my parentheses. Now let's look at this term by itself right here. Let's do a quick little scratch work. I'm going to get on my other board. If we're actually attempting to find limits of this x natural log of x over x taking this separate limit as x going to positive infinity, then this is itself right here an indeterminate infinity over infinity. That means we can use the L'Hopital's rule, okay, to come up with a new set of functions, a new quotient here. It's a 1 over x over 1, and take the limits for this as x approaching positive infinity, and that gives me this overall is a 1 over x, take limit as x approaches positive infinity. Okay, so all that here is actually a 0. So go ahead and pause the video if you have to, and take note carefully with this little scratch work, because all of that here, now assuming you're back from pausing the video, all of this here is useful for, now I can conclude that this little work right here, if we go with limit laws right here, this work will become 1 minus 0. Okay? So in the end, it's actually, we don't even have to do anything with L'Hopital's rule except for that little step I've done here. So I had to manipulate the L'Hopital's rule to find that the limits for that particular little term right there. But now, putting it all together as one big problem, well, again, let me just briefly remind, this infinity came out from the limit of that function x when x approaches infinity. And then each one of these inside, simply because we applied basic limit laws and distributed our limit symbol into each of these problems. The constant term remains the same. That's we've proven over there on the other board to be a 0. So all together, really this is just infinity times 1, which is really not indeterminate. Now we can tell the answer. Infinity. All right. And so now our final answer for this problem is, so we did have some L'Hopital's rule being used here, but I mean, it's just only on one of the little steps right here. The answer here is a positive infinity. All right, and that's how we've done this problem as well. Okay, so that's all I plan to have for example 4 right there, where, you know, the two problems in example 4 reflect the situation where you have an infinity minus infinity. Okay. And now let's look at example 5 here. Let's evaluate. All right. And example 5, I am going to introduce the first problem. How about let's find limits as x is getting to positive infinity of x, but raised to the 1 over x function. Okay, x raised to the 1 over x power. I said function, but that was incorrect. X raised to the 1 over x power, like that. So what I see now is that, think about the limit laws. If we apply that here, then we're looking at this will give us, you see, when x gets large, this x by itself will go to positive infinity. But this 1 over x will go to 0. So we actually run into that one of the indeterminate form that I introduced earlier. It could be either 1 to infinity, okay? It could be a 0 to 0, or it could be infinity raised to the 0 power. This one of ours is that one. Okay, so, but again, L'Hopital's rule does not apply here yet, okay? So now, generally, any of these three forms of indeterminates here has a power being, you know, basically it actually came out from this one function, but raised to another function, okay? And then we take the limits, some limits, okay, and then either to a value, right, or to an infinity right here. But then see, this can be the case where f goes to 1 and g goes to infinity. That can be the case where f goes to 0 and g also go to 0. Okay, and then this indeterminate form can be the case where f grows to positive infinity but g goes to 0. But any one of these three forms came out from this original form with a function being raised to a power being another function, and that's what I I want to emphasize right there. And so here's how we can tackle this now. And the trick I'm about to show you is actually, we call it a trick, but it's actually a quite commonly and really a lot more commonly used than the earlier method I've shown when we were in the other kinds of the indeterminate forms. So in example 3 and example 4 I showed previously, the techniques being shown there are not as commonly used as the one we have here. So this is the technique I'm about to show here. At our level here, being quite a beginner into calculus, then this technique is a little bit cheating in a sense that if later on, if any of you take the same course in calculus but in a much more in-depth level that normally universities call these the real analysis courses, then there are a lot more arguments into this. But here it's widely accepted for beginning calculus students level over here. We can just assume, and that's the part where I'm saying it's a little bit erroneous here. I mean, let's say if the answer here turns into a value L, if that limit here is an L limit, okay? And so when you go to a much more advanced course in this, the same kind of problem, but you have to start defending yourself how you can know that it will go into a limit. We don't need to get that complicated here. Just here say, let's say this limit here exists and go to a value L right there. Then here's how we can argue. If that limit here go to a limit L, then I can take seeing this as an equation, I am now going to take the natural log of the left-hand side, which is the natural log of the limit problem. It's a natural log of the limit problem, x to the 1 over x. Okay? And then, but on the right-hand side is the natural log of L. All right, everybody good with me on that? And so here's the thing. Logarithm itself is a continuous function, so taking the logarithm of a limit is also the same as just the left-hand side here. Nothing much to be done with the right-hand side now at this point. But this overall problem means the same as, it's the same as the limit as x get to positive infinity of, now I can swap the logarithm and the limits here. So now it becomes logarithm of x to the 1 over x. Okay? But what's the advantage of doing this? What's good about doing this? See, we have learned that since logarithmic differentiation, and we've learned that through deriving a lot of functions using logarithms. But the idea is logarithm can bring a power down in front and take away that power and only leaves a power 1 here. And so now that means that in my next step, this expression here turns into a 1 over x times natural log of x. Okay, and that here equals natural log of L. And then here we still remain having a limit problem as x is approaching positive infinity. All right, we are really close to the victory here. So here's the thing. Pretty much natural log of L is gonna be the same for the next many steps. So how about let me pay all of my attention to this left-hand side here. So now I'm just gonna go ahead and pay my attention to only find the limits on this left-hand side. Okay, so the limit on the left-hand side is a natural log of x over x now, if we're writing that all together in one fraction. And so we have seen this limit problem earlier. This is where we can quickly see that there's an infinity over infinity indeterminate form. L'Hopital's rule now can apply here. So I mean, I'm talking about now if we just pay all of our full attention to the left-hand side. And so now, and so that means I'm kind of branch off a little bit, bend the direction, the direction a little bit. And so now I'm going to apply L'Hopital's rule here, so just like that, like how we have done that. It never hurt to repeat that kind of problem again. But L'Hopital's rule says, according to the L'Hopital's rule, okay, then we can go 1 over x over 1 here, derivative of the numerator over derivative of the denominator, and take that overall as a new limit problem, but the two results will turn out the same. Okay, and so this is now going to be just overall 0, because this overall, I shouldn't rush like that. How about it's a limit of a 1 over x, okay, as x is getting to positive infinity. And that's how it's now 0. But now, just because we found a successful limit, so I made that mistake earlier. When I came to this, I became so excited and I thought I was done. But this is not quite done. This is only the limit that's equal to the left-hand side. Okay, our left-hand side here is this limit 0. But we'll remember our limits here, our main goal is to find out what L is. Now let me remind anyone viewing my video here, our main limit is to find, our main problem is to find out what L is, and L is playing in the role of our limits for this overall problem. This 0 is only the successful limits for our left-hand side after we have done all that logarithm trick, like that, taking log of both sides. Okay, so now on my other board. All right, so, but now what I can see is the left-hand side gives me a limit 0. And that needs to be equal to natural log of L on the right-hand side. Okay, and so the remaining trick is just solve for L right out of this equation. And yes, you are required to already master your skill in how to solve a logarithm equation like this, but it should be simple for a student already arrived at a calculus course right here. This is the same as L equals e to the, because this is log base e. So log base e of L equals 0. That means L equals e to the 0. L equals e to the 0. So that means L equals 1. And I should have written that in this way. So L equals 1. So what have we found here? What we have found is that our beginning problem was x raised to the 1 over x, and we were taking that limit, okay, and we were saying, let's say the limit here equals L. So now we just found out what L is, so L equals 1. So this overall limit here equals 1. That is our answer for that, okay, and that's how it works and so the trick here, the generality for this kind of technique I want to point out here is that, so when you have a function f of x and being raised to the power being another function right here and being asked to find a limit, it could be a limit to a limit point A. Doesn't always have to be to infinity. But the point is, this setup here brings you into one of the indeterminate form. Then you're gonna just simply start out by thinking of, hey, if that limit here turns out to be a value L right here, then we're gonna take natural log of both sides. Okay, natural log of that limit on the left-hand side, the f of x raised to the g of x right there. Okay, and then on the right-hand side is natural log of L. And then we proceed on, bring that limit inside here, and so we can bring the g function out front and all that. And then eventually at some point we're going to solve, if that limit on the left-hand side here turns into a successful limit, we are going to solve for L out of that logarithm equation. Okay. And so that's how this common technique, and surprisingly, it works quite effective out there. It works quite effectively out there. All right, so I'm going to spend about a minute or so to erase the board, and we're heading out to the last problem in example 5 here. All right, so the last problem that I have prepared for everyone is here. So it's part B, okay? And here we want to evaluate the limits as x approaches 0 actually. And it's not a sided limit, it's an actual limit. X go to 0 here, and 1 minus 2x, okay, raised to the 1 over x right here. All right, so before we really get into this problem, I want my viewers and also that includes the students who study with me to be cautious on this problem a little bit, because yes, a lot of times people are going to rush into seeing that, hey, x go to 0, so this overall grow to infinity. This 1 over x grow to infinity as x go to infinity as x go to 0. Okay, and so people from there, once they see this observation, then they're gonna rushly see this as, and yes, as x go to 0, then this inside here is go to 1, so 1 to the infinity. So and in that way we got our goals expressing this, seeing this as an indeterminate form right there. But we got to be more careful than that, because in this problem maybe it turns out like that, but you know, whoever went this way already left out one important thing right here. This is x going to 0, but from both sides. Okay, x going to 0 from both sides. So really, if we recall from one of our very first problem, this limit here 1 over x when x go to 0 from both sides is actually a does not exist. Just that. But I'm not talking about the whole problem. So I'm not saying that the whole problem does not have a limit existing. I'm just saying that if we go just that direct route right here, as x go to infinity, go to 0 here, then the 1 over x supposedly turns into a DNE. Okay, and so that's making it even harder for us to decide. But here, when we actually face challenges like that, then we can always have our choice of breaking the problem into two separate sided limits. And if the two-sided limits agree, then we have a final limit. If the two-sided limits do not agree, then the overall limits problem is a DNE. And so with this problem, I am going to first consider the same problem here, but as a left-hand side. Okay, I am going to think about the same problem here, 1 minus 2x. Raised to the power 1 over x. I'm going to take the limits, but now x go to 0 from the left-hand side. Okay. And so for this one right here, then yes, here's how it works. Well, direct limit law says if we're letting x go to 0 from the left-hand side this time, and this term go to 0, this 2x terms go to 0, and so that's 1. And as x, your 1 over x function is as following. Okay. And so as x getting close to 0 from the left-hand side, we are going to negative infinity. So it's something like that. You see what I'm saying? So that means it's now in one of our indeterminate form. That is now where we can start applying the common trick that we have seen in the earlier problem. Now for this thing, I'm going to say, hey, if that goes to some L value. All right, and so now from that point on, just like how we applied the trick we have done earlier, I am now going to take the natural log of both sides, x going to 0 from the left-hand side of 1 minus 2x to the 1 over x equals the natural log of L. Okay, and so that means in my next step, allow me to write my next step in a little small narrow space of the board here, but we're looking at natural log of, and now it's a 1 minus 2x to the 1 over x. Okay, and then we're taking that as a limit problem, letting x go to 0 from the left-hand side, and then all of that there is supposedly equals natural log of L. Okay, and so the advantage of doing logarithm on both sides now is just like how the previous problem was carried out. Then 1 over x multiply in front, and now we're looking at natural log of 1 minus 2x, but just now power 1, simply just that. All of that there equals natural log of L. And here we're still taking limit as x goes to 0 from the left-hand side. So the left-hand side expression here on my equation is still showing, I can still reduce it down further. 1 over 2x, 1 minus 2x inside of natural log over x, if we write it into one fraction. And then all of that equals natural log of L. And take the limit as x go to 0 from the left-hand side. So I'm trying to use the algebra to simplify it down as far as I can before it's really ready for getting an actual limit. And so now I can see that if x go to 0, the denominator here go to 0. And what I mean here is that if we just specifically focus on the left-hand side now. Now let me switch to this board, take some time to erase my board, and then we're going to have all this spacious area here. Okay, so you see, so now if we just pay attention on that natural log of 1 minus 2x over x, okay, and taking the limits as x goes to 0 from the left-hand side. So denominator here is clearly going to 0. As basic limit laws can imply that. Now basic limit laws also say, and logarithm itself is a continuous function, just like back in the days how I made that argument when we learned about these fundamental limits right there. And so it's now logarithm of 1 minus 0, which is now altogether 0 over 0. An indeterminate where we can apply the L'Hopital's rule here. Okay, so that now means according to the L'Hopital's rule, I can now go ahead and take the derivative here, which gives me the derivative on top is a 1 over 1 minus 2x, but multiply with negative 2. And then the denominator here gives me just 1. And so it's a completely brand new problem at the same limit point right there. But each one of these came out as two separate derivatives from our previous function. And so now with this one here, and we can think of that ugly looking mess here as it's a negative 2. Okay, it was a negative 2 over all that. And so altogether this limit here on the left hand side is a negative 2 over 1 minus 2x. Taking the limit as x goes to 0. Okay, so this limit here as x now go to 0 in the denominator. Well, the numerator now is completely free from the x variable, independent with the x variable. So it stays now 2 minus 2 according to basic limit laws over 1. So it's negative 2. Bingo, we found some working and successful limits. But now sadly that's not our final answer. Recall again, all that here we're doing is only the answer to this left hand side work right here. So that means that negative 2 is not our answer yet, but it's easy to get to the actual final answer now. That means we're looking at minus 2 is equal to natural log of L. Minus 2 is equal to natural log of L. So that means now we can find out what L is. And recall for yourself, L is our left-hand side limits. Our limits here, as x is getting close to 0 from the left-hand side. Okay, and so now to find the value of L, I can just simply raise both sides to the e power. So L now equals e to the minus 2 power, and that will be our final answer right there. Okay, so L equals e to the minus 2, or you can algebraically think of that as the 1 over e squared. Okay, all right, but here's so much work, but that was only for the left-hand side of the same limit. We already found we came to 1 over e to the negative 2 power. So now I'm going to have to also consider the right-hand side. So let's see what the right-hand side can give us. But pretty much the work will hopefully we'll pick up pace a little faster because we have already had most of that built right here. So from the right-hand side, the same function, 1 minus 2x to the 1 over x. Okay, we take the limit as x goes to 0. But now this time from the right-hand side, that's what the right-hand side limit is. Okay, and so now I can see that this is as x go to 0 from the right-hand side, and we're looking at now 1 to the positive infinity. And this is that's indeterminate form again. And so, but now to handle that, again, just like how we've done it earlier, I'm going to say if it was equal to an L value, if it would be equal to an L value, then now I'm going to take natural log of on both sides, so natural log of L on the right hand side, the natural log of all that limit work, x going to 0 from the right hand side of 1 minus 2x raised to the 1 over x. That's what it is. And then so the rule for limits, I mean the rule for taking logarithm of the limits, now we can bring the limits outside. And then now that becomes a logarithm of 1 minus 2x raised to the power 1 over x, okay, equals natural log of L. Okay, and so now I can bring the 1 over x down. So it's on the left hand side. I'm looking at limits problem. X go to positive, go to 0 from the right hand side. It's up 1 over x, and now we have seen this in the earlier part. So this expression, go ahead and let me pick up pace a little bit. Natural log of now 1 minus 2x over x equals natural log of L. Okay, and so now this one here, if we consider the limits individually, okay, so think about just pay our focus, our attention to this part right here. So that's natural log of 1 minus 2x right here over x. As x goes to 0 from the right hand side is actually now another 0 over 0 indeterminates, where we can now apply the L'Hopital's rule. So I'm again gonna take a minute or so to erase my board here, and we're gonna quickly navigate over here. All right, so now on my other board, now seeing that this limit of natural log of 1 minus 2x over x, as x is getting close to 0 from the right hand side, is an indeterminate, then now L'Hopital's rule says that result here will be the same as the result on this following limit: 1 over 1 minus 2x times negative 2, okay, and over 1. Each one of these came out as the derivative of these two corresponding functions right here. And we take the limit as x goes to 0 from the right hand side. All right, and so now I can go ahead and rewrite all that as one fraction. So minus 2 over minus 2 over 1 minus 2x. And we're taking the limits as x is approaching 0 from the right hand side. And so this is now simple enough for us to just go through the basic limit laws and get an answer over here. That term 2x in the denominator will go to 0. So now we're looking at minus 2 over 1 again, which is negative 2. But keep in mind again, this is not our final answer to this problem. This is not our final answer to this problem. It's only just whatever the left hand side here. That's, I put the little rectangular box here. Okay, so supposedly now, right from that expression I was just pointing out, the negative 2 is supposedly to be equated with natural log of L right here, and L is our actual limit. So that means now finding L is just going to be a simple step away. One simple step away. L equals e to the minus 2 again. E to the minus 2. E to the minus 2. So this is what we have found. And so now putting the two results together, and this is what I meant by the two results together. All right, so let me now spend a minute, because we are so close now. All right, now I have to remind any of my viewers, this limit at start was a general both-sided, two-sided limit. We already consider the same problem here, 1 minus 2x raised to the 1 over x power, but as a limit when x approaching 0 from the left-hand side, we came to the existing limits being 1, let's keep it this way, being e to the minus 2. Okay, it's a finite value. And just now we finished with same function, 1 minus 2x being raised to the power 1 over x, taking the limit as x approaching 0 but from the right hand side. So this right hand side limit here also came to e to the minus 2. Okay, and so now since left hand side limits and the right hand side limits agreed, then now we can go back and say this overall answer here equals e to the minus 2 right there. And that's how we find the answer to this particular problem. Okay, and that's all I have for this example number 5 right here. And I hope that gives enough problems for viewers and particularly my students to see through as many different kind of problems as possible. But again, as I said, I highly recommend that outside of my own video lessons here, go ahead and hop onto the internet and learn from other professors to see how they carry out their own kind of problems out there. Okay.